Hello and good afternoon, morning, evening, depending on what time you are doing this lesson. We are going to be talking about 10.1 today, exploring quadratic graphs. And basically, I want to remind you that quadratic refers to the x squares that we've been doing. We've been factoring quadratics for a while. So this portion of the quadratic function should look normal to you, ax squared plus bx plus c, but it has now a y in front of it. You might remember that when we graphed lines like y equals mx plus b, you needed to have the y there. So good news is we're not going to start off with the really crazy ones. Not that I want to scare you or anything, but we don't want to get you too worried yet. I'm not trying to worry. I'm probably worrying you more by saying all that. But anyway, ignore all that nonsense. Just keep in mind that a quadratic function has three terms, but it can also have just one term. And so what I've done right now is I've put on the board the most basic quadratic function, which is y equals x squared. This would assume that the a value was a 1, so then you have 1 times x squared is x squared. B would be 0 and C would be 0. So that means that you would get this smaller, simpler function, if you will. And so in order to get started with all this, I have to kind of give you guys an idea of what a quadratic function looks like, what the parent graph looks like. And this is generally what we consider the parent function. It's the function that basically fathers all. And with functions, what happens is that once you know what one of them looks like, all of them pretty much look the same. They just might be fatter, skinnier, taller, shorter. It's kind of like when you think about family. It isn't always the case, but a lot of times when you, like in your family, you might have a trait, some certain type of nose. Maybe all of your family members are tall, or that kind of thing. And it's kind of like all of your relatives will kind of have that same general look to you. And that's kind of what's happening with this. It's a family of functions. So all quadratics have basically a shape of parabola. It's called a parabola. And I'm going to show you right now what that looks like. So what we're going to do first, we're going to have a t-table so that we can graph this. And I'm going to have a generic x values here. And we typically always want to have some negative values, 0, and positive values. So I'm going to use -2, and if I plug it into this, and you got to be careful that when you have -2, if you're going to use the calculator, you want to make sure that you put it in parentheses, like this, -2 squared, because if you don't, the calculator will tell you the answer is -4, and it's not -4, it's actually +4. And that should make sense because -2 times -2 is +4. And then -1, if I plug that into x, would be -1 times -1, which is +1. 0 times 0 is 0. 1 times 1 is 1, and 2 times 2 is 4. So very quickly we create this this table of happiness, this table of basically ordered pairs that we're now going to graph. So, or plot. So -2, 4. By the way, I don't make my t-table. I know I did it right now because I did it ahead of time. But I don't usually make my t-table until after I've gotten these values so that I know how big to make it. Since the biggest x value is +2 and the smallest x value is -2, then I don't really have any need to go too far on my x-axis. And since the biggest y value is 4, then I don't have to worry about getting too crazy or too high on my graph. I'll have room for everything in this grid here. So anyway, -2, 4 is going to be -1, -2. +4 is 1, 2, 3, 4. So basically, it's going to be right about there. So I put my little dot right about there. That's -2, 1, 2, 3, 4. So I'll put a little dot there. And then -1, 1 is going to be -1, 1 is going to be right about here. 0, 0 is going to be right here. 1, 1 is going to be right there. And then 2, 4 is going to be 2 and 4 right about there. Now what you should be noticing right now is what we call symmetry. If we think of the y-axis as like the middle of the graph, then you'll notice that whatever's on the right-hand side is also on the left-hand side. So this point here is there and this point is mirrored there. And this is what my graph looks like. I connect it with a smooth curve. And this is what a typical parabola looks like. So it's curvy, and there's some things about it that I have to describe to you. There's this little thing called the axis of symmetry. So I want to point that out to you. Parabolas always have basically an imaginary line that I can just go like this. That kind of goes right down the center of the graph, if you will. And we call this the axis of symmetry. It basically means that if I were to fold, and I can't fold it because I can't really fold my board here, but if I were to be able to fold the graph along this dotted line, then you would get mirror images on either side, a reflection, if you will. And so that would be my axis of symmetry. Typically, that line is a vertical line, and it's always x equals some number. In this case, since the x coordinate is 0, the axis of symmetry is x equals 0. Another thing that you want to know about these graphs is that they all have what we call a vertex. And a vertex for a parabola is this point right there. The vertex is basically the bottom of the graph. It's the highest or the lowest point on the parabola. So this little guy right here, this little point right there, is called the vertex. And if the parabola looks like this, then this would be the lowest point on the graph. So then sometimes we call that the minimum. Not sometimes, we always call it the minimum. So the minimum is the lowest point on the graph. But sometimes parabolas can be upside down, so they can look like this. And in that case, this would be the vertex. And because this would be the highest point on the graph, then this would be what they call a maximum. So just some vocabulary for you to know. We want the general shape of the parabola. We call this kind of like an upside down umbrella. So we don't need any umbrellas around here because it's so hot, the sun is like blaring. But it reminds us of an umbrella, and it's upside down. So that's kind of what it looks like. And that shape is called a parabola, just so that you know. A parabola, I know it's a weird word, but that's what we call that shape. So you have to know that it's a parabola. You have to know what the axis of symmetry is. It's going to be the line that goes right down the middle. It goes right through the vertex. The vertex is this point here. It's the highest or the lowest point on the graph. And if it's the lowest point, we call it a minimum. If it's the highest point, we call it a maximum. So as long as you have all that information, then you should be okay with most of your homework today. So, examples for you. Here is example numero uno. Identify the vertex of each graph. Tell whether it is a minimum or maximum. So it's a very simple problem. What you have to look for is the lowest or highest point on the graph. So, in this case, this guy right here is the lowest point, and because it's the lowest point, we're going to call that a minimum. And we use the x and y axis to give the actual coordinates of the vertex. So we use v for vertex. And this x coordinate is 1, because it's 1, 2, 3, 4, 5. So this is 1, so the x coordinate is 1. And I have to go down 1, down 2, so the y coordinate is negative 2. And just like that, you have your minimum, or you've answered part A of this question. Then it's a minimum, and the vertex is 1, negative 2. So do the same thing over here. This is kind of a funny looking shape. You can now see how the parabola can get upside down. It kind of looks like a little igloo kind of shape thing, maybe. This is like the roof of the igloo, I guess. But basically, that's kind of the shape that you have here. So again, we're looking for, in this case, the highest point on the graph. And because it's the highest point on the graph, this time it's a maximum. And then we have to give the coordinates. So here's 0, so I'm going to go negative 1, negative 2 for x. And then I'm going to go up 1, up 2, up 3, up 4. So it looks like the maximum in this case is negative 2, 4. And that's pretty much as hard as that is going to be. So I will have you guys do this example now. And then we are going to go here. And now we're going to get to the nitty-gritty, which is kind of like the harder part of what we're doing. Not that it's extremely hard, but it's the harder part. Is that's graphing a quadratic function. So what we want to do is start with the t-table. So we're going to come right over here and we're going to make a t-table. And again, we're always going to start -2, -1, 0, 1, 2. It's always a good place to start. And we're going to go ahead and plug these x values into the function. So we're going to get y equals 1/2 times -2 squared, because that's the x value. So -2 times -2, we said before, is +4. So I'm going to get 1/2 times 4. And 1/2 times 4 is actually 2. So I'm going to get 2 over here. And then we're going to do -1. So y equals 1/2 times -1 squared. And -1 times -1 is +1. So we get 1/2 times 1, which is 1/2. So here we're going to put 1/2. And then 0 is going to be 1/2 times 0 squared. So 1/2 times 0, which is 0, because 0 times anything is 0. And then you're going to start to see that symmetry happening, because 0 is generally the middle. And so you'll see that on the left, and I say left because if you're looking at the x-axis over here, here's 0, and -1 and -2 are on the left. So because parabolas are symmetric, whatever happens on the left should happen on the right. So I'm going to guess right now that if -1 was +1/2, that +1 will also be +1/2. And that if -2 was +2, that this +2 will also be +2, because it has to be the same thing on both sides. But we're going to confirm that by doing the math. So 1/2 times 1 squared, and you get the same thing. 1 times 1 is 1. So you get 1/2 times 1, and you get the same thing that we got earlier with the -1. So we get 1/2 again. And then we're going to have y equals 1/2 times 2 squared. And again, because it's 2 times 2, we're going to get 4, which is the same number that we got earlier when we were doing -2. We got the 4 here. So 4 times 1/2 is 2. And you get the same answer that we did earlier with the -2. So this is going to be 2. So now we're going to graph that. And we're going to have -2, 2. So here's -2. Here's, we're going by 2s here. 2, 4, 6, 8, 10, as you can see there. So we're going to go -1, -2, so make sure that your scale, make sure that you're following my scale here. I'm going by 1s here and by 2s on the y-axis. So to go to x -2, I'm going to go -1, -2, and then my y is going to be +2, so it's going to be right there. And then I have -1 and 1/2. And actually, I'm going to change my scale because I don't really think I need all the way to 10. So I don't really know why that's there. We're going to stick with the 5. So I'm going to go 1, 2, 3, 4, 5, and then -5. And I'm going to go ahead and re-graph that guy. So instead of having the scale be by 2, I'm going to go by 1. So I change this to 1, 2, 3, 4, 5. So what I'm going to do is I'm going to go -2, 1, -2, +2 is 1, 2. So we're going to be right about here. And then we're going to go -1 is 1/2. So if this is 1, 1/2 is right about here. And then we're going to have 0, 0. And then we're going to get the same image, 1, 1/2. So you can see how they're the same on both sides. And then 2 is going to be 2 up here. And again, they're the same on both sides. So when we connect it, in this case, we have a minimum. And the vertex is 0, 0. And the axis of symmetry is going right down the middle. So that's how you graph this quadratic function. All right, so you can now graph this little guy. And then we will go to this example. And this example, don't let it scare you. What I've done is I have graphed 3 different functions, and they all have different coefficients, like they're all x squareds. This is just a regular x squared, and you've got 1/4 x squared and -4 x squared. So we're kind of curious to see what happens how does the graph compare when you have a regular x squared? What happens when a number goes in front of it? What if that number is like an integer, and what if it's a fraction? Like, how does that affect the graph? What happens if it's positive? What happens if it's negative? And hopefully we'll see that here. Again, so it's asking me to use these graphs, so I'm going to provide you with the graphs. It says order the quadratic functions, and it has 3 quadratic functions, -4x squared, 1/4 x squared, and x squared, from widest to narrowest. Okay, so in the end, they want us to see which one's the widest and which one's the narrowest. Now, obviously, you can probably tell that this is the widest, And then we've got, second widest is probably going to be this guy right here. And the skinniest or the narrowest is probably that one right there. Okay? But before we get to that, I just kind of want to, use this example to also tell you a little bit about how I know that, okay? First of all, let's talk about negative. Here's positive x squared. And we said earlier, that's this graph right here. We said earlier that positive x squared is the parent graph. This is what the normal graph looks like, okay? So this is the main graph. And you can tell that it's facing up like a umbrella upside down. So it's facing up. So it's opening going up. And then we look at this one over here, the negative 4x squared. And not only is it skinnier than that one, but it's actually facing down. It's opening down. So basically the rule of thumb is if you have a negative in front of the x squared, it's going to flip it over. It's going to make it face down. And secondly, if the number in front of x squared is bigger than 1, okay, so 4 is definitely bigger than 1, it's going to make it skinnier, okay? And if you have a fraction that's not bigger than 1, so 1/4 is basically 1 out of 4 pieces. So if you had all 4 of the pieces, it would be 4/4, and you would have a complete cake or pizza or whatever. If you have 1/4, it means that you don't have the whole thing. So obviously it's smaller than 1. So and if that isn't good enough for you, if you're still not sure, like you don't know if it's bigger or smaller than 1, don't be ashamed. Just go to your calculator, type in 1 divided by 4, and if you get 0 point something, it's not bigger than 1. So if this number is smaller than 1, then it's going to make the graph really wide. So this green one is a lot wider than the normal graph, okay? But because it's still positive, it's still facing up. So just wanted to point that out, that negatives make it go upside down, and numbers that are larger than 1 make them narrow, and numbers that are smaller than 1 make them wider. So to answer the question, we should probably do that as far as ordering them from widest to narrowest. The widest one is right here. So we would put f of x equals 1/4 x squared. The second to widest or whatever, sorry, I should put f of x there. The second widest is this one right here. And that's just the standard f of x equals x squared. And then the narrowest of them all is the negative 4x squared. So f of x equals negative 4x squared. Now the reason why I'm saying that to you is because you didn't have to graph all 3 functions to figure this information out. At least not anymore. Before I told you what I just told you, you didn't know how to tell which one was narrower or wider. But when you get to the example that you're going to do, which is this one, it is not necessary for you to graph all the functions. All you have to do is look at the numbers in front of the x squareds. Okay? Is the number in front of the x squared bigger than 1 or smaller than 1? And that's going to tell you whether or not it's wider or narrower. So based on that, you can order these functions from widest to narrowest. And then we have our last example. And again, this time we're going to be graphing again, and we did that earlier, but this time we're going to be graphing something that has a +3 in it, so we're going to compare those graphs. I kind of want to show you how that's going to work. So we're back to our t-table for that. And I'm going to do x, y, and the first function is y equals 2x squared. And I'm going to plug in my normal numbers here, -2, -1, 0, 1, 2. Again, I'm going to assume that this is going to be the middle. So whatever I get for these numbers, I can repeat for this on the bottom. So I'm going to go ahead and do this verbally. I'm not going to write it all on the board because we don't have enough space. But I'm going to go ahead and plug in -2 for the x squared. So -2 times -2 is +4. And then that times 2 is 8. So we're going to get an 8 there. For the -1, I'm going to go -1 times -1 is +1. And +1 times 2 is 2. And then 0 times 0 is 0, and 0 times 2 is still 0. And then 1 times 1 is 1, and 1 times 2 is 2. And then lastly, we have 2 times 2, because it's 2 squared, so 2 squared is 4, and 4 times 2 is 8. So those are my numbers. Again, you can see how they're the same, and they're the same. Okay, it's supposed to happen. If that doesn't happen when you're graphing, or when you're writing your table, then something's wrong. That's a quick way of knowing that something's not right in your graph. The second thing we're going to do is all over again. We're going to have x, and this time we're going to graph, or we're going to plot y equals 2x squared plus 3. okay? So it's a different equation. We're still going to have the same x values, but this time we're going to get 2x squared plus 3. So when I plug in negative 2 times negative 2, get positive 4. 4 times 2 is 8, and 8 plus 3 is 11. Plug in negative 1, I get negative 1 times negative 1 is positive 1, times 2 is 2. 2 plus 3 is 5. 0 times 0 is 0, and then 0 times 2 is still 0, and 0 plus 3 is 3. 1 times 1 is 1, 1 times 2 is 2, 2 plus 3 is 5, and again you can see how they're both 5s. This is still the middle, even though it's a 3, not a 0. This is still the middle, you got 5 and a 5, so I'm going to guess that this is going to be 11. But we can plug it in. 2 times 2 is 4, 4 times 2 is 8, 8 plus 3 is 11. And you have that symmetry happening, okay? Another thing that you should probably notice is that these two equations are pretty much the exact same thing, only in this case you're always adding 3 to the y value. And that should make sense because if this y value was 8, if I add 3 to that, I get 11. If I add 3 to 2, I get 5. If I add 3 to 0, I get 3, and so on and so forth. So you can see how all that's really happening is that you are adding 3 to the previous values. So we're going to see how that pans out in the graph. And so first I'm going to graph this guy. So I'm going to do it in green. So you'll notice also that I already made my grid, but I kind of did this ahead of time. So I already knew that my values were going to be 8 and 11. So you can see how I went on my y-axis. This is my y-axis over here. For my y-axis, I need to go all the way up to 11. But I don't need any negatives on the y. There's no negative y numbers, okay? So I don't really need a lot of the negatives. So I only put 2 numbers there. And that's just because I don't really need to use them. And then I'm only going to go to negative 2 and to positive 2, so I didn't go very far. So it's pretty important that you do your t-table first and then do your grid, because once you know what the numbers are in the t-table, that'll determine how big you need to make your graph, okay, so that you have enough space on your paper. So anywho, that being said, we're going to graph this guy. We're going to plot these points now. Negative 2, 8. So this is negative 2 right here, negative 1, negative 2, negative 3. And then 8 is right here. You can see I already kind of marked it. So here's 8. We're going to go negative 1 and negative 2. And I want to get this right. So I'm right there. Okay? Then we're going to have negative 1, 2. So here's negative 1, 1, 2. And then we have 0, 0. And then, of course, it's symmetry. So we're going to have 1, 2. And 2 is going to be 8. They're going to be on the same side. And this is what your graph looks like. Okay? So now we're going to graph the other one. And what you're going to see is that because we're adding 3 to all the y values, all that's really going to happen is this whole graph is going to move 3 units up. Okay? So negative 2, for example, negative 2, 8. But in this case, it's negative 2, 11. So this point is going to move 3 units up to the 11. Okay? The negative 1, which is at 2, is going to move 3 units up, 1, 2, 3, which is at 5 now. So this is 1, 2, 3, 4, 5. Okay? 0 is going to move 3 units up to 3. The 1, which was at 5, sorry, the 1 which was at 2 right here is going to move all the way up to 5. Oh, sorry, it disconnected. Let's let it come back here. So at 1, we're going to be at 5. You back yet, Pen? There we go. And we'll undo that thing that I just did. Okay, so there's my point there. So this point moves 3 units up. This one right here moves 3 units, 1, 2, 3. And then the last one, which is 2, moves, which is right here at 8. That's where it was. Now it's going to move 3 units up to 11. And you're going to get a graph that looks like this. So it's pretty much the same graph. In fact, if I picked up the pink graph and moved it down, it would be right on top of the green graph. So they're basically the same thing. So it says to compare the graphs. Basically what you're going to say about that is that the 2 graphs are the same, but that the 2x squared plus 3 is shifted 3 units up for that. So, so let's see, we're going to go y equals 2x squared plus 3 is the same as y equals 2x squared, but shifted 3 units up. So you could expect that if it had a -3, it would shift the graph 3 units down, okay? Or if it was a +5, it would shift it 5 units up. If it was +7, it would shift 7 units up. If it was -9, it would shift 9 units down, and so on and so forth. So that is how you do that. And you are going to do this example here, comparing these two graphs. And then once you've done that, you will have completed the notes for this lesson, and I will see you in class. So good luck.